So welcome back to this week's lab. So this week's lab, we want to implement the BRAM and program the BRAM using the processor, the Zynq processor, and the SDK. In a couple of labs ago, we had actually just used the BRAM only on the FPGA, the PL part, but now we want to program the BRAM using the the SDK and the processor that is in the Zynq board. We will start by just creating a new project. We go next. We'll choose a directory for our project. And then we can just choose a name. So I'll just call this lab 9. We go next. And then after that, you can just choose the board. Make sure that the board is the Zywood Z710. This is the board that we're using. Next and finish. So then now that this has happened, we have to create a block design. So we can just keep the name whatever, and then we can just open the block design. Now we have to add the Zynq processor system itself. So you just add the Zynq processor system. We can just run block automation. This applies to the board presets. And now we need to make a few changes in the processing system itself. Unlike last week's lab, we actually want most of the PL configuration to the PL clock, the PL reset. So what we'll just do is we'll change a few of the peripherals that we have. So we don't need Ethernet, USB, and SD cards. We can just remove these and just click OK. Next, we'll add the BRAM controller itself. So we add the BRAM AXI BRAM controller. We can just run connection automation for this. Select for all three, and then we just run that. If we just double tap here and we can just regenerate the layout, you can see this in much more detail. So what's happening is that this BRAM block memory generator is actually using a native port. So we want a way for communication between the AXI type ports that we have on the processing system and the native port that we have on the BRAM. So how's that achieved? Using this BRAM controller. This essentially takes in an AXI input and converts that to a BRAM native output so that the BRAM itself can understand where to program. So we'll have to change a few settings here. So we'll open the block memory generator, changes to single port RAM. And that's the only setting here. We can just rename the actual block itself here. So we can just call this VRAM. And yeah, that should be fine. And here we have to open the AXI BRAM controller. And we need to change the protocol to AXI Lite and the number of interfaces to 1, as we only have one single port RAM. So once that's done, you see that the actual run connection automation also got removed. So a few more IPs are here. This AXI Smart Connect. This AXI Smart Connect is essentially a multiplexer. So it takes in one single GPIO input that has the address and the data, and it knows and it is able to send the signal to the various IPs that are connected via the Smart Connect. So if the address for the BRAM controller here is found in this GPIO port, it'll route the connection from here to here. Else, if there's some other address here, then it'll route the connection somewhere else. And this processor system reset is just a simple reset. So it just takes in the PL resets that we had and PL clock that we had here, and it makes that that is usable by the PL itself. So this peripheral reset A is given here, and that's the reset. So we can just save this. Then we can just open address editor. So this address editor is the location of our BRAM control, and this is the location where we want to actually write our data. So if you want to use the BRAM, so we'll look in more detail about this in the SDK component. Next few steps are quite crucial. So we need to first validate our design. So make sure there are no hanging wires and something like that. This is a critical warning. This critical warning is due to the size of the actual design itself. As we have a small design, this will not create an issue. So you can just ignore this. You can go to sources, right click on the BD file, and you can create a HDL wrapper. Once that's done, we can go to file, export, and export the hardware. We can go to file, export, and export the hardware. Before exporting the hardware, we need to first generate our bitstream. So you can just click on generate bitstream and let the bitstream generate. So now that the bitstream has been generated, we want to just open the implemented design to compare with what we saw last week. So if you remember last week, we had no PL component. So that's why there was nothing actually being written on the PL fabric. But now that we have something there, we can see that there is a PL component, and we can see that. So if you aren't able to see these routing wires, make sure that this box is enabled routing resources, and you'll see these wires. So these are the two processes that we have. This is the routing connections, and this is the BRAM implemented on the PL fabric itself. So yeah, you can just close this. And then we can go to File, Export Hardware, include the bitstream, then export it. Once that's done, we want to launch the SDK. So you just launch SDK from here. Go to File and launch SDK, and wait for the SDK to open up completely. Right, so now that is done. We can see that our BRAM controller is also present here. And now we can actually write the code to program this. So in order to do that, we first need to create a new application. So we do an application project. We just name this. I'll just call this BRAM on SDK. Make sure there are no spaces in any location or directory. That creates an issue. The OS will be standalone, and the hardware platform will be the design itself. So we just go to next and choose the hello world application and just finish. So now what we want to do is we want to modify the BSP settings. So we just click modify BSP settings, go to standalone, and in the stdin and std out, we want to change this to the core side that we did last week as well. And then we can click OK. Now we want to actually add the hardware server. So we can just add the hardware server, and we'll show once that's done. So before continuing with the hardware server part, I'll just show a few more things with respect to the source files here. So the BRAM and SDK, so under the BRAM and SDK project directory here, the source file would actually have the hello world program that we want to run, which is this. And then it has a bunch of binaries itself. So these binaries are are the ones that actually help us program most of our components. Okay, so now we'll continue with the programming part. So as we saw before, that these are the header files that we have. These are various binaries. So we want to use these binaries to actually be able to program the board itself. So I'll just copy the code, and you can walk through it step by step. So the include, but this is just a simple input output C basic header file. This platform.h is something that's specific to the SDK, and it just helps in initializing and clearing the platform later on. Parameters.h is something which is new, we have to include this time. This helps us keep all the information of the various addresses, the various locations of the IPs that we have used. You can also find the parameters.h IP here in the BSP settings. So the BSP has the include folder, and the include folder X parameters would be available here. So as you can see, this is essentially just storing all the addresses of all our values itself, which is quite useful when you want to program large block designs. Next, we have this ZIL.io. ZIL.io is also found in the same folder here, this ZIL.io. ZIL.io is essentially helps us to send and receive the data. So as we want to send 32-bit data and receive 32-bit data, we will use ZIL.io. ZIL cache is here for clearing the cache, but it might not be necessary in your case. Next, we have the main function. So first just initializing the platform, and we're keeping that the data in is this vector here, this array. We want to then initialize the address, the initial location. So as you can see, this is an actual error here. And how do we fix this? If you have an error like this, you can just go to the parameters.h file, look for the BRAM address. So the BRAM address would be here. So you can see the peripherals definition for the BRAM control. So depending on what you had named your BRAM control, I did not change the name. I left the name as just AXI BRAM control 0. So you can see that this is the location for that, and we can just see that the base address is this, which matches the address editor we had earlier. So we can just copy this here, go back to our C file, and then just paste that there, and do the same for this part. And if you just save that, the error goes away. So this is the initial vector, initial array. This is the initial address. Next thing, what we want to do is we want to run a for loop. So this for loop is essentially going over all the contents of our array, and it is writing to this location, this init address location, and it is writing this value. So this data in value at I. So it's writing this value at this location, init address, and we are just changing the init address by adding 8 to it. 8 being because it's a 1 byte address, we just want to change the address location itself. Next thing, what we want is you actually want to read the data. So you can print just the data writing has been done, and then after that we can print the location itself. So we want to actually see what the contents are. So for that, what we do is we use the zil in 32. So we had a zil out 32. Now you can use zil in 32. All this would need is just an address. So how do we calculate this address? We calculate this address here. So we took the base address, we added an 8 into the address that we want to index we want to look for. 8 because we added 8 here. So we want the third index being 8. So we will just add 8 into the index. So hopefully that is clear. So if you have an address stack, you can see that if you had the base address and you add 8 into the index, you would reach the location for this 8 uh, vector here, this 8 point here. And then we have finally the cleanup and the return. So now in order to get this working, we first need to add a few breakpoints. So what we can do is just for things, we can just move this back down, and I can just add a breakpoint here. So this is right after the data out has been completed. So this data out, we can see from our variables tab later on that the data out will have the variable and the value that we want to use. So now what we want to do is we want to just debug our entire system and actually test it. So we can just go to here, we can go to add. Next thing, what we can do is just name this Zybo 192.168. Make sure you have in use symbol server on, test the connection, and then we can click OK. Next, you want to right click on this BRAM and SDK part, go to debug as, and we can go to debug configurations. Yeah. So now we want to use the system debugger. We want to reset the board, and we want to program the FPGA also. And make sure that the application itself is what we have here, that there are no other applications running. We can just click on debug, and this will just launch the debug perspective. So now in theory, what should happen is that the code should start and then it should just stop at this print statement, and we should see the data out being written. Okay, so that now that the debugger has now been on, we can just really just make sure that all of our breakpoints are now set properly. So what I have is I have a breakpoint only at this location, this printf location. So once the data out has been written, this breakpoint would just program would stop at this print statement, and we can just see the data out there. So again, we see at the third index, this is the 8 value. So we should see the value 8. And that is exactly what we see here. So you can see that the data out has this value 8, which is the third index, 0, 1, 2, and 3. And that's what we see here. So that is it for this part 1. Um, we will continue with part 2 later.